But wait, what if we didn't want a charged complex ion, but instead a neutral compound? How are coordination compounds formed? Well, first, coordination compounds contain one or more complex ions and associated counter ions of opposite charge to maintain the neutral coordination compound that we'll see. So let's go back to some of the compounds we saw with Werner. So of course, we have our brackets that are going to have our complex ion in it. We have our charge on the outside, which is +2. To balance out the charge of the complex ion, we have our counter ion, which are going to be our chlorines. And so we need 2 of these negative charges to balance up the 2 positive charges so that we can get a neutral compound. So the neutral compound is called the coordination compound. Okay? And this is also the neutral compound over here. Now, of course, again, this coordination compound is made up of this complex ion here and these counter ions. So the complex ion is what you see here, and it's surrounded by different ligands like our 5 NH3s and our 1 chlorine group. And then the counter ions, of course, like we're saying, are on the outskirts. Okay, you can also do the same thing with the other compound that we saw from Werner. You have our complex ion here with a +3 charge, so we need 3 counter ions to balance out that charge. And once the charge is balanced, you can write out your coordination compound. We mainly see coordination compounds that can exist as a cation coordination complex, and of course an anion counter ion, or we can have the complex ion being anion, for example. So you start off with the cation and a complex ion that is negatively charged. Okay, so again, you normally see coordination compounds where you have the complex that's positively charged attached to a negatively charged counter ion, which we see here. But we also can have, when you're going to have your complex ion be an anion attached to a positive cation, which you see at the bottom here. Now, of course, you can have complex cations that are going to end up having positive charges and then, of course, form compounds with negative complex anions, but we don't really talk about that in this course, okay? We're going to focus on these 2 main ones. The ones where we have a cation complex with an anion counter ion, or a anion complex with the cation counter ion, okay? But no matter if the complex ion is a cation or you have the counter ion as a cation, either way, you're going to write the cation first, okay? So it's always going to be written before the anion, so it's always going to be cation, anion, and then the charge of the cation is always going to be balanced by the charge of the anion, or, of course, whatever opposite charge, vice versa, okay? Now, anytime we look at ligands, like when you have multiple ligands here, neutral ligands like our amine are going to be written first before our chlorine. And so a lot of times you have, and the reason because of that is because the amine group is actually in alphabetical order. So A is going to come before chloro, which is C. And so that's another reason why the amine groups are written first. And because they're neutral. And of course, you need to just make sure that the counter ions are always going to be outside of the bracket. And we can go between coordination compound and then dissociate it into the complex ion and counter ion to help us visualize what happens in aqueous solutions as well. So let's go ahead and look at this one here. We have the cation as a counter ion, which is going to be K+. So that means this entire complex ion has to be a minus charge in order to form this neutral complex. So this whole thing is going to be a minus charge for this complex ion. Same thing here and here. This entire complex is going to be a +2 charge, and then the chlorine is going to be that -1 charge, and of course there's 2 chlorines here. This entire complex is going to be a +3 charge, and then of course our chlorine, going to be 3 of them, that's going to be the minus charge. So you can kind of disassociate them into their ions. And remember, the complex ions kind of act as polyatomic ions in aqueous solutions, so they kind of stay as a group and stay bonded to one another. So let's sort of put this all together. The whole goal is to make sure you're doing your flashcard moments. We've been seeing them kind of flashing throughout. Make sure you're stopping and kind of organizing yourself with the information. So when I say put it all together, that means complex ion, counter ions, ligands, oxidation states, and then finally neutral coordination compound as well, okay? So let's go ahead and answer this question. Give the coordination number and charge of the central metal ion in the following coordination compound. So he wants to give the coordination number and the charge of the central metal ion. So first we want to assess each of the complexes here. And as you can see, we have our counter ions and the complex ion here, counter ions and the complex ions here. So as you can see, we're dealing with coordination compound. But in order to get the coordination number and the charge of the central metal ion, or simply the oxidation number, we want to make sure that we just disassociate these into the complex ion and the counter ion, so we know to basically isolate that complex ion on its own. So let's go ahead and do that. So here the complex ion is going to be VnOH4, okay? And of course, this entire thing is going to have a 2- charge. Why? Because sodium, we already know, is going to be a +1 charge, and there's 2 of them. So if there's 2 sodium +1 charge, that means there has to be a 2- charge on the complex ion here. Okay, we broke that one down. Let's go ahead and do this one. We know that our potassium is going to be a +1 charge, and there's only one of them. So we're going to have our potassium. That means this entire complex has to be a -1 charge. Okay? We've got H2O2 and then C2O4 2. This whole thing is -1, just so we can balance everything. Now, the next thing you want to do is consolidate all the different ligands in your complex ion. So that means we're only focused on these complex here and, of course, this complex here. So that means I'm going to be focused on this OH ligand and then this water ligand and this oxalate ligand. So these are all the ligands in these different compounds. Okay. So what information do we need about the ligands? We need to know their denticity, how they bond to the central metal ion, and we also need to know their charge for the oxidation number. So if we get our denticity, we can get the coordination number. Okay. So if it's denticity, and then if we get the charge, we can get our oxidation number. Okay, again, of these different ligands. So let's go ahead and look at our OH group. The OH group has a -1 charge, and it is monodentate. So if it's monodentate and there's 4 of them attaching to the zinc, that means you're going to have a coordination number of 4. Okay. Now, as far as oxidation number, we would basically solve for our zinc. So we're going to have X plus 4 OH minuses. Each OH is going to have a -1 charge, and this entire thing is equal to 2 minus. So you're going to have X minus 4 is equal to 2 minus. We're going to add 4 to both sides. Our X is going to equal to a 2+ charge. So that means the zinc here is going to have an oxidation number of +2. Let's go ahead and do this one over here as well. We got to focus on our different ligands first. So we have a ligand for water, and this is going to be neutral, and it's also going to be monodentate. Then we have the ligand for oxalate, and this is going to be a 2- charge, and it's going to be bidentate. So when we're thinking of coordination numbers, we have to figure out how many things are surrounding this cobalt. So we know there's going to be 2 waters. There's 2 times water, and they're each monodentate. But we also know that we have 2 attachments of this oxalate. So because this oxalate is bidentate, we're going to have 2 times 2, which equals 4. So there's going to be 4 plus 2. There's going to be 6 things surrounding that cobalt. Now we got to do oxidation number. Okay. So oxidation number is going to do what we did before. This entire thing is going to be equal to -1. So we're going to have our cobalt, which is our X, plus 2 times 0 because we have a neutral water, plus 2 times -2 is equal to -1. Okay, so we're going to have X minus 4 is equal to -1. Add 4 to both sides. X is equal to +3. So the oxidation number here is going to be +3. This is how you will kind of go about answering these questions. It's all about, again, kind of isolating the complex ion from the counter ion, focusing on the complex ion, and using the ligand information to help you get coordination number and oxidation numbers. Okay, so although you're not responsible for naming coordination compounds like you would organic compounds, it can still be important to kind of orient your brain. So why not a quick review? First things first, we already know the cation is going to be named before the anion. So here we have our complex ion as the cation, and here we have the counter ion as the cation. Either way, they're going to be named first. And also within the complex itself, they're going to be named in alphabetical order, okay? So all these ligands are going to be named in alphabetical order. And of course, when you have the neutral ligands, they're going to go first. A lot of times you will see common names for some of these ligands. So instead of like water, the actual common name is aqua when it comes to naming coordination compounds. So you can see some of those tiny discrepancies as well. And also when you have like an anionic ligand like our chloride, you're going to end up dropping the IDE and replacing it with an O. So here we have chloro instead of chloride, and that's how you end up naming things with those ligands. Also, when it comes to the different ligands, there can be different amounts. So like if NH3 has 4 and this chlorine has 2. So if there's 4, it's going to have the prefix tetra, and for chlorine, it's going to have the prefix di. And these prefixes are definitely not going to be a part of the alphabetical portion of naming those ligands in alphabetical order. And also, just like we see with naming, we definitely want to have our transition metals have the parentheses with the Roman numerals to dictate the actual oxidation state. Okay, so when we do have the complex ion as the cation, which we see here, and when you have the complex ion as the cation, we end up writing the counter ion with the ending of IDE. So if we put all this together, we're going to take our complex ion and first name the actual ligands in order, in alphabetical order. So we have amine, and then we have chloro. Next, we put the amount of each ligand. We have tetra, so 4 amines, and then we have dichloro. Finally, we end with the transition metal cobalt, and then we have to know the oxidation number of cobalt, which is going to be our 3 here. How did I end up getting the oxidation number? Well, I went ahead and looked at my overall coordination compound here. So I know that this metal ligand complex has to be plus because we have a chlorine that's going to be a minus charge. So the entire complex is going to be equal to a minus charge here. So again, we have our complex ion, which is going to be plus because we know our chlorine is going to be minus. So this entire complex is equal to plus 1. So you have X, you're going to add it to 4 times 0 because we know that the amine group is going to be neutral. And add that to 2 times minus 1 because we know the chlorines are going to be all minus 1. This entire thing is set equal to plus 1. Okay? So you're going to have X minus 2 is equal to plus 1. You're going to add 2 to both sides, and you're going to get X is equal to plus 3. So our cobalt is going to have 3 in Roman numerals to dictate its oxidation state. And of course, we end just naming the actual counter ion and writing it out as chloride. And then finally, when you have the counter ion as your plus charge and then the complex as your anion, then that means you're going to have to write out the actual counter ion first, which is potassium. And then you're going to go ahead and name the complex ion like we saw before. So you want to make sure that you have all of your different ligands. So we have water, bromine, and chlorine. So we have aqua, bromo, and chloro. Then we're going to put the amount. Water is just 1, so it's just straight up aqua. There's 3 bromines, so it's tribromo. And there's 2 chlorines, so it's dichloro. And then at the end, you're going to write the transition metal, cobalt. But the only difference is anytime it's going to be, of course, having an anion as your complex ion, you have to end your metal in ATE. So you have to kind of write your metal and then end the name in ATE and then write the Roman numerals. So up here, when you have your complex ion as a cation, you don't have to end it in ATE. You just write cobalt and then in parentheses 3 to dictate the oxidation number. But down here, when you actually have your complex ion as an anion, you must end it in 8 and you have your Roman numerals after that. So this is cobaltate, meaning it's definitely an anion and it's still going to have an oxidation number of 3. Okay, folks? And of course, just for extra practice, we can go ahead and get our oxidation number just by knowing what these different counter ion charges are in complex ion. So we have our cobalt here, which is going to be our X, plus 0 for water, plus 3 times minus 1 for bromine, plus 2 times minus 1 for chlorine, and this entire thing is equal to minus 1. Now, as we said before, you'll be having to go to your ligands page to go ahead and break down what each of these ligands are and get all their charges. So it's going to be X minus 3 minus 2 is equal to minus 1. Okay? Wait a minute. This entire thing is equal to minus 2, folks, not minus 1. I'm tripping. So that's minus 2 and minus 2. Why is it minus 2? It's because there's 2 potassiums here. And so if there's 2 potassiums, that means you needed 2 positive charges to go ahead and balance out 2 negative charges from the complex anion. So sorry about that. So you're going to have X minus 3 minus 2, which is going to be X minus 5 is equal to minus 2. Make sure I have a better view there. Okay, X minus 5 is equal to minus 2. Add 5 to both sides. So our X is going to equal to plus 3. That means our cobalt here is going to be plus 3, which is why we have plus 3 in those parentheses. Again, you will not be tested on this, but hope it helps you visualize the concepts better, not feel overwhelmed when you see these compounds come your way.